Hello, we UIU Mars Rover Team presenting our third generation rover Yggdrasil for the System Acceptance Review for URC 2024. Our team of 43 members from different academic backgrounds has been working relentlessly to upgrade Yggdrasil from its predecessor, Telos. Over the past 7 months, our team has undergone a collaborative effort dividing into 6 sub-teams to meticulously develop reliable and modular subsystems for our rover with adequate quality assurance. Experience gathered from the NTRS last year, we tested Yggdrasil in competition-like settings to make sure she is ready for this year's competition.
Our newly modified carbon fiber chassis subsystem with its 3D printed wheels ensures maximum suspension and traction in the competition terrain. The wheels are lightweight and more sturdy than the last version for their unique gyro structure. The rocker bogie suspension with a rear differential bar mechanism significantly improved the stability of Yggdrasil, ensuring space maximization. We have introduced a brushless motor-driven lightweight steering mechanism for enhanced maneuverability, allowing the rover multiple degrees of freedom. We have designed multiple courses to evaluate Yggdrasil's unparalleled capacity to retrieve and deliver objects in the most demanding environments, assisting astronauts in their critical missions. The courses include terrain and obstacles similar to those we encountered in the last year's competition, such as traversing over rocks, grassy fields, sand surfaces, rocky areas, steep inclines, and vertical drops. The rover's arm is capable of quick and easy manipulation of both heavy and light objects, such as towing and lifting a 10 kg payload, and as well as picking up small objects such as screwdrivers, hammers, and various shapes of rocks. This year we have upgraded our wrist mechanism to a direct drive semi-differential module for precise control over the end effector. 6 degrees of freedom arm is capable of opening a drawer and inserting and removing a cache from it. Additionally, it can perform sophisticated tasks like inserting a USB flash drive, handling an electrical socket, push buttons, flip switches, turning a joystick, typing on a keyboard, and tightening a screw. Our center-aligned parallel sliding end effector allows the arm to pick up objects having various geometrical shapes at micro-precision regardless of the fragility of the objects. We evaluated the arm thoroughly on a configurable lander to achieve competition readiness in the equipment servicing mission. Also, from our previous experience of manipulating small objects, we have utilized YOLO V8 model to detect push buttons, switches, pendrive docker, and small joysticks with inverse kinematic to semi-autonomously assist with the manipulation. Furthermore, our companion drone ICARUS assists our mission by detecting unique rock samples from above. Moreover, we extended the evaluation of our rover with some fun and challenging situations, such as making coffee and delivering it.
We have implemented autonomous navigation through our own raw stack to ensure minimal resource consumption. We have upgraded our previous GPS receiver to an RTK module for better geopositioning. The override system allows us to take control of the rover in emergencies. With a simple failure recovery system, if the rover fails at any point, it can autonomously return to the previous location and continue the mission. The searching algorithm has been optimized to search arco tags and objects in a wide range. On arriving at the GNSS coordinates, the rover goes into a spiral search pattern to locate the arco marker or a specific object and then navigates towards the target. Our hybrid path planning system uses a 2D LiDAR for localization in the dark, and in the daylight it creates 3-point cloud maps and segments areas using a depth camera for precise localization. We have tailored our obstacle avoidance algorithm to reroute the path to avoid obstacles. However, in an emergency, it backtracks to avoid collision. Our newly added pothole detection model facilitates to avoid deformities on the terrain. Our rover's dashboard is equipped to monitor its current state, path, and target distance as well as coordinates of arco posts and objects. Moreover, we have created an application that can analyze the given waypoint image and transfer the corresponding coordinates to our navigation system. Our object detection model is developed exclusively to identify standard water bottles and orange rubber mallets. It seamlessly detects objects up to 16 meters away. This robust object detection model empowers the rover to navigate towards its targets with pinpoint precision effortlessly.
The easily swappable customized battery module along with the internal system monitoring and hybrid cooling provides a runtime of 2 hours while ensuring the optimal temperature. A kill switch has been implemented for the emergency stop of the rover. For real-time data transmission, we utilize a 915 MHz directional and omnidirectional antenna on the base station to communicate with the rover up to 2.5 km. Additionally, a 5.8 GHz communication system is employed for real-time video transmission.
This year, we have redesigned our science subsystem to eliminate cross-contamination. Our newly designed science module has a 4 degree of freedom manipulator and a scooping claw for subsurface samples, and this sensor module aids habitat analysis. Our rover installed Bifrost lab targets 3 biomolecules: protein, carbohydrate, and chlorophyll. Automated tests include anhydride, Benedict, and UV test. Qualitative color changes are streamed back to the base station as the input to our multiple biomolecule detection-based algorithm. A science dashboard integrates real-time feeds, GNSS coordinates, panoramas, sample data, and post-analysis results, facilitating life presence assessment. Our rover's camera captures sedimentary structures analyzed by CNN for layer recognition and geological interpretation, aiding depositional, environment, and water history analysis. A silt regulate collector mechanism is implemented to collect a sample with scientific interest at a depth of 10 cm or deeper for further analysis at the base station.
We have assessed Yggdrasil in environments similar to the competition for the best preparation of the controllers and system-level fault testing. With rigorous preparation, we strongly believe that we can perform well and thrive in the competition. UIU Mars Rover Team conveys the best wishes to all the participating teams and look forward to meeting you all in Hanksville this summer.